All right, in this video we're going to talk about how to set up the finite element analysis or stress analysis in Inventor. And this is a real basic how to do this. This is by no means a full explanation at all. But to go ahead and set this up so you can actually run some tests on your parts is the first thing you have to do is go ahead and assign your materials. So I'm going to hit this material button at the top of the screen here. That's your little checker ball here, and you want to go ahead and apply that PLA material that you went ahead and built up in the last video. So with that applied, you can see the color changed, and you can tell that we now have a PLA material assigned to the part. Now, unfortunately, unlike a 3D printed part, this is a solid part, so it's going to be slightly different as far as what we're going to be getting out of this for results if we were actually going to test this hook, but we're going to go ahead and set this up and see how this works. So we'll hit the stress analysis button over here, and if you have any analyses previously set up, you'll see them here, and if not, you're going to get this dialog box for creating a new study. What we're going to do here is we're going to keep that static analysis. We're not going to change that. Later on, we'll talk about using a shape generator and how we can analyze where stress is moving through a part, but for now we're just going to stick with static analysis, and we're going to go ahead and hit OK. Once that's done, we start moving our way down this browser list. And the first thing is the material, and you want to jump in just to see that the original material is what you're looking at. That's PLA. And you can override it if you want to see how this would perform with a different material. I believe that PET is loaded in here as a plastic you can take a look at. Let's see, yeah, there's PET plastic. So you can play around with some other plastics and the like, but there's also bunches of metals. So for now, we're going to keep this straight, hit OK, and now we're going to get into constraints. So the constraints would show up if we had any, but we don't. So we're going to go ahead and hit the fix button, because all I want to do is hold this thing from moving. And I want to turn this thing because my hook is going to actually be held right here on that surface. So that's how it's going to be held. It's going to be held by another hook at that point. And we'll go ahead and apply that and then cancel. And then you can come over here and hit that plus. You can see I have that constraint set. So the next thing we'll go ahead and do is add force. So we grab the force button here and close that because that's what it normally looks like. And then I want to go ahead and press select this surface, and you can see that glyph showing that the force is going to be applied in that vector. So that's all set and good. We'll go ahead and set this up as just 100 newtons to get started, and we'll hit apply, cancel. And now we are ready to go ahead and run our simulation. So we select run simulation, hit run, and you can start to look at some of the results. Now you can see that there's several different results over here in your browser. The first one that pops up here is von Mises stress. This is set up in megapascals, and you can see that the max is at 20.64. This is all really based upon the material tensile strength and the settings for tensile strength. So you really have to understand what those are in order to interpret this information. So we got to jump out to the web and take a look at that. So I'm going to jump out here to MatWeb. This is material property data, and you can find a lot of this information you need out here. And we're going to slide down here and this is, you can see here for PLA. We're going to slide down here and start looking for the information on tensile strength. So coming down, there's mods of elasticity, elongate, film tensile strength at yield, tensile strength ultimate. So the ultimate tensile strength, sliding across here, and we're going to look at this average of 47.2 megapascals, and let's find the yield, tensile strength at yield, and slide across, and here is 38.0 megapascals. So this is the yield. This is where it goes into a plastic state, and then of course the ultimate tensile strength. So 47.2 or 38.0 is where it's going to start to bend and not go back. And then this is 47.2, so we're going to start looking at fracture. So we jump back into here and look at, we're at 20.64, well below both of those numbers. So this thing should come back to its original shape once it the load is gone. So I'm going to actually look at the actual deformation here, and this is important to take note of. in that this actual versus the adjusted, this is the actual movement that is predicted given the load that has been put onto this part. So obviously if you think it's only going to move this much, yeah, it's not going to then, deform the part permanently. It should go back to its original state. That's also what the tensile test information is telling us versus the von Mises stress. Now, first principle is also a stress test that is focusing on tensile strength, and generally they're very close together, von Mises and first principle. So you also have to understand that tensile strength to understand what this first principle is telling you also. Now, third principle is a little different. Third principle is looking at the compressive forces of the part. So we're going to turn this so you can see here that the blue forces here are the greater forces, and that the third principle stress is actually giving you a negative number as the information we really want to know, because it is focused on the compressive nature. So the colors are reversed and the numbers are also reversed. So here we're looking at that 10.99 as the maximum compressive strength on the back side of this part. Get into displacement. We even showed you this a little bit already, that as the load is applied to the part, as the load is being applied down here, that's what's going to happen as far as this part moving in that particular direction. So not a whole lot of movement actually, but the adjusted, you can see as you adjust this more, my gosh, you can make this thing look like it's going to have some type of horrendous activity, but it doesn't seem like it's really going to do that. And safety factor here is the higher the numbers, the better the safety factor. The lower the number, the worse the safety factor. Anything 1 or lower is where you really want to start looking at a redesign of the part. So obviously with the numbers that we're pulling here based on the tensile strength and safety factor and the like, you can see that the part should really hold up fairly well by putting 100 newtons of weight, which really isn't a whole lot of weight, on this particular plastic part. So hopefully this is a quick down and dirty run through the material analysis part here in Inventor. By no means is this a comprehensive look at this tool at all. This is just how to get started. Hope this helps.